Hey, what's up, people? We're going outer space style with the black background, but luckily, I hope the ones I sent you have a white background. Takes a lot of printer ink to make the black background. Anyway, what we're trying to get at in the next couple of weeks, that much, something like that, I guess, is this question, or at least this is one of the big questions we're trying to get at. All right. In general, how fast does the space shuttle have to go to stay in orbit? Well, it depends on a few things. Um, Really, it only depends on one thing, to tell you the truth, um, if we're talking about orbiting the Earth. But, why is the space shuttle able to stay in orbit at all? Well, one big thing we should hopefully be able to tell by looking at, this pretty simple animation is that when that space shuttle is in orbit, it moves in a circular path. Now, it might be well, no, it is a circular path. Um, and that means that its direction constantly changes, which means that its velocity constantly changes, which means it's accelerating, which means there has to be an unbalanced force or a net force acting on this object. Well, that force in this case is a gravitational force. Oh, how awesome is that, by the way? The green on the black, that's what I'm talking about. So there's a gravitational force. I'm actually going to write it as Fg. All right? And that gravitational force really is what this little subsection of the unit is about. This unit's on circular motion and gravitation. So this actually, we're going to start with the gravitation part. All right, we want to look at gravitational forces, how big they are, what affects how big they are, that's really it for this few pages. All right, so the concept, not too hard. Some of the problems can get hard. Obviously, you've seen how that works, but the math here pretty straightforward, I hope, or at least the physics pretty straightforward. The math, the algebra, blah blah blah, can get a little more complicated. All right, so yes, it's via a gravitational force that things stay in orbit. All right, it's via a gravitational force that that we stand here on Earth. All right, so let's look at how big those forces are, or how strong they are. And let's look here. One of the big ideas is we think of the Earth attracting us. The Earth attracts bowling balls to the Earth, right? But the question is, what objects are attracted by gravity? The answer, I hope is it up here? Oh yeah. The answer is every. Yeah, the red might be even better. Every two objects in the universe attract each other. I'll even write that. Attract each other. Hence, we call this phenomenon, let's try the blue. Oh, that's pretty sweet. You might not be able to see the blue so well, I wonder. You have to turn off the lights. That's part of this. I didn't tell you that. You got to turn off the lights for this unit. Universal gravitation. All right? Everything attracts everything else. I mean, really, literally. Every object in the universe right now is pulling on you. Every object in the universe. I am currently, no matter where you are, no matter where I am attracting you with a gravitational force, right? The sun is pulling on you right now. The farthest star in the universe right now is exerting a gravitational force on you. It's pretty darn small, but it's there, all right? Your computer is exerting a gravitational force on you right now. Every two objects in the universe, okay? Now, how big is that force? It depends. Let's look at a couple of situations here. Let's look at three pairs of masses, and let's figure out, now, what we're assuming here is assume that a larger size object means a more massive object, all right? So we have pair 1, pair 2, pair 3. The question is, which one do you think, which pair feels the same, feels the largest gravitational attraction? So think for a minute. or maybe take a vote, put a check mark somewhere, or just be a completely passive observer. Don't do that. So which pair feels the largest gravitational force of attraction? It is pair 3. Pair 3 feels the largest gravitational attraction. All right? And then why is that? Well, the deal here is, I'll say, more total mass, more gravitational force. All right. Well, what does that mean mathematically about how gravitational force works? Well, it could mean a couple of things. It could mean that gravitational force is proportional to, well, if there's two different masses, we call them M1 and M2. It could be that gravitational force is proportional to the sum of the two masses. Or it could be that gravitational force is proportional to the product of the two masses. Well, it happens to be this one. Oh gosh, back up. All right, and that's what we say. You might even want to write this down. Gravitational force is proportional to the product of the masses M1 and M2. Product meaning multiply them together. Okay? Now, if we're actually going to draw these forces, these objects exert a force on each other, right? So here's a force pair, right? They exert equal and opposite forces on each other. Now, up here, these objects, like we said, well, they're going to exert a smaller force because there's less mass. But again, each object exerts the same exact force on the other. It doesn't matter that one of the objects is bigger than the other. They both exert the same exact force on the other. And the third group up here, they would each also exert the same exact force on each other. It's going to be smaller because each of their masses is smaller. All right, but this is the one people goof up, right? I mean, I hate to say it, but this will be a question on a quiz or a test about two masses, one a lot bigger than another, and they'll even give you numerically, mass 1 is 50 times mass 2. Compare the forces they exert on each other. Somebody's going to say, well, the force that one exerts is 50 times the other. It's not. The forces are always equal and opposite. Always, 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 right? That's Newton's third law. That's force pair stuff. The forces that two objects exert on each other are always equal and opposite. That's a make or breaker on, that could be, right? One little question for a 4 or a 5 on the AP exam. Okay? Hopefully it's a simple one. Okay, now, so here's one thing that we have for the relationship, or one relationship that dictates how gravitational force works. Here's another. Let's look at 3 more pairs of masses. And now we've kept mass the same. All right, now I'll go back to that in a second. But all these have the same mass, so that's not a factor anymore. But now what we have is their separations are different. Okay? So the question is, which pair feels the largest? I don't know if which pair feels the largest gravitational attraction? All right, so think for a minute, take your vote, enter your answers. The answer is pair 1. All right, and why is that? Well, because gravitational force is inversely proportional to what we call R. And R is separation of masses. I'll finish that in a minute. Well, sorry, I'll be grammatically correct right now. It's separation of masses. All right, now, notice here, I kept the masses the same, but changed the separation. If we go back here, well, I kept the separation the same, and I changed the masses. So what separation are we talking about? Well, we're talking about from here to here. There's R. All right, so R is not from, edge to edge. R, by definition, is the separation of masses is, now I put that this thing back in there. Separation of masses, center of mass. All right, it's how far apart the centers are, not how far apart the edges are. So if we have, an object here and an object here, they're not 0 meters apart. They're whatever this distance is apart. Fair enough? Okay. Now, it actually doesn't work out that it's just inversely proportional. It's an inverse square relationship. And why is that? I don't have a good answer for that, to tell you the truth. I think, I'm not going to just try to sound like I know why. But I can find out. You can find out. Yeah. Anyway, oh yeah, what does it mean gravitationally? Sure. Well, I guess what I probably should have put in here is closer objects, it, leads to more gravitational force. And this is what's supposed to go up here, right? That Fg is inversely proportional to the square of the separation. All right, well, we can combine the last two things, because those are the only two factors that affect how much gravitational force exists between masses. The only two factors are how much mass each one has and how far apart they are. All right, so that means that we can put, this equation together and say that gravitational force is m1, m2 over r squared. Okay? There's a problem with this, though. The problem is, one of them is that, F is measured in newtons, right? So here's a newton. And so far over here we have, mass times mass would be kilograms times kilograms. And R is in meters, so that would be meters squared in the bottom. And as you know, a newton is not a kilogram squared per meter squared. Okay? That's one problem. The units don't work out if this is our formula. The other problem is, imagine taking two 1 kilogram masses, right? You know that brass kilogram mass we have hanging around here. Take two of those and put them a meter apart. They will not exert a 1 Newton force on each other. 1 Newton is a force that we could feel, right? That's a reasonable sized force. They do not exert that much force on each other, which means that the numbers don't work out just right either if this is the whole formula. Well, the way we take care of that is we put in what we call G, capital G, not lowercase g, not lowercase g meaning acceleration due to gravity. We put in capital G that we call the universal gravitational constant. And that universal gravitational constant does two things for us. One, it makes the numbers work out. It's a constant of proportionality. Two, it makes the units work out, right? And so the units, well, first of all, I'll say that G is, by definition, 6.67 times 10 to the negative 11th. So that takes, remember what we set up here? You have those two 1 kilogram masses, and you put them 1 meter apart. Well, the force would be G times 1 divided by 1 squared. The force would be this much, 6.67 times 10 to the negative 11 newtons. That's how much the force would be, right? So how do we turn these kilograms and kilograms squared per meter squared into newtons? Well, the units of G are Newton meter squared per kilogram squared. All right, so check it out. If G has these units, Newton meter squared per kilogram squared, well, let's see, the kilograms and the kilograms go, the meters and the meters go. Oh yeah, we are left with newtons, right? So that's what G does for us. It makes the units work out right. It makes the numbers work out right. I'll just try to clean this up a little bit so you can see the equation. Yeah. Okay? You do not need to memorize G. You never need to memorize constants. Constants will be provided for you with their units. You should memorize equations. Okay? Okay, onward. Now, I don't know why I didn't do a, well, I do know why, but we're going to jump right to what we call a multiple mass problem. You know, if we go back a couple of pages, maybe to here, yeah. So, you know, we looked at some single mass cases, or sorry, not single mass, but two mass cases, where we just have, you know, one object exerting a force on the other, and therefore the other exerting a force on the first. So those are pretty straightforward. Let's look at some, you know, I guess more multiple mass systems. Really, I mean, in this case, three mass systems. And let's look at how forces act on different objects. And in this case, let's look at the net force on the object in the middle. All right? Well, we don't know what this object's mass is, the blue one, but what we do know is the two objects that exert forces on it have the same mass. However, we can see that this R, I don't know, let's call that, if we do like, we'll call this mass 1, and we'll call this mass 2. How about that? So this we could call R1, and this we could call R2. You can tell that R1 is bigger than R2. Right? So since gravitational force depends on mass and separation, well, the mass is not a factor, because no matter what this mass is, you know, the masses pulling on it are the same mass. However, the distances they are apart are different. And since the red mass is closer, it's going to exert a larger force. I would call this force that 2 exerts. It's going to exert a larger force than this, the force that 1 exerts. Make sense? Now, if we wanted to find the net force exerted on the blue one, we would call it F2, not 3, F2 minus F1. Right? Just like we've done before. Net force statements, no brainer. All right. Example 2, we put the separations the same, R1, R2. Again, we're calling this 1 and this 2. But now the masses are different. And here, I mean, if we have twice the mass over here, it's going to exert twice the force. Right? So I can do my best here to call F2 twice F1. All right, so a couple things we could say here. We could say, 1, that the net force is still F2 minus F1. We could also say that F2 is 2 times F1. So if we wanted to be, you know, super fancy, we could say this is 2F1 minus F1, or that the net force is just F1. I know, we might be getting ahead of ourselves, but not the worst thing in the world. Okay? Okay. Third, let's see, where could we put a blue mass? And questions will sometimes say this, other than infinitely far away. If something's infinitely far away and R is infinity, then the force is 0. But where can we put a blue mass between these two, on a line between them, such that the net force on it is 0? Or really, we're saying where the net gravitational field is 0. So think for a minute. You ought to pause and think, where could you put another mass such that there's 0 net force acting on it? Pause for a minute. Think, maybe even put a little mark down. Well, the answer is we'd have to put that mass somewhere over here. All right, and the reason is, well, here's my kind of thought process. This mass, mass 1, is a smaller mass. Typically, it would exert less force, but we're closer to it, so maybe it exerts more force. And mass 2 over here is a bigger mass. Typically, that would mean it exerts more force, except we're farther away from it, so it'll exert less force than it typically would. So we get a F2. Now, it's not as big as it should be, is it? We get an F2 like that. There we go. And somewhere in there, yeah, the net force is 0. Fair enough? You get it? Okay. Now, yeah, this G. Where does G come from? Well, first, now, we should know, you don't need to know this, but Einstein, not Einstein at all, Isaac Newton came up with universal gravitation. In the same year that he came up with his 3 laws of motion. Oh, yeah, and calculus. Although there was a Russian guy that also came up with calculus maybe a couple years earlier. Yeah. So anyway, pretty busy year for Isaac Newton. I believe he had just graduated from college, moved back home, and came up with calculus, 3 laws of motion, and universal gravitation. So not bad. When I got out of college, I also moved home, and I painted fences for a few months. So kind of the same thing. Not really. So anyway, G. Newton postulated what G should equal. And then experimentally, it was able to be verified by a pretty neat experiment by a dude named, I believe, James Cavendish. And what he did was he suspended a bar, a rod, right here, from a torsion wire. And a torsion wire, you can sort of imagine as just a 2-dimensional strap. All right? You know what a bandsaw is by any chance? A bandsaw is a saw that, well, the blade is just one continuous loop of steel that's wrapped around 2 big wheels. And the band has a certain width and a certain length, but its thickness is pretty small compared to either of those. And what you can imagine is if we hung something from this strap, really imagine from that bandsaw blade, well, you could twist it, right? But it would take some force to twist it, and that band itself would do its best to bring bring itself back to equilibrium, right? And so this band, what we call a torsion wire, has some value K that refers to how many newtons of force it takes to twist it a certain number of degrees. Okay? So what Cavendish did was from this torsion wire with a known value of, I don't know, a torsional something or other, known torsional constant maybe, he literally, on the end of this bar, he put 2 masses that he knew, and near those he put 2 real big masses that he also knew, and literally the gravitational force between masses big M's and little m's pulled these masses over a certain number of degrees. And because he knew how many newtons of force it took to bend that or to twist that torsion wire per degree, he figured out what the gravitational force was. And since he could measure how far apart they were, what the force was, and he knew what the masses were, he was able to back out to find G. And he got it within a really, really high degree of agreement with what Newton postulated. And here's what I say to all my kids every year. If you can build a Cavendish experiment and from it prove that, and the proof might involve me coming over to your house or the place where you built it, show that you can find G within a factor of 100 I'll give you a guaranteed A for the fourth quarter. Guaranteed. 95, fourth quarter. It takes extreme isolation from outside stuff. It takes extreme precision in measurement. It takes a lot of patience. It takes a pretty good amount of effort, and it's an awesome experiment. So if you're up for it, I'd love to see it. No one's ever done it. Everyone says they're going to do it. They never do. So here's a super simple example. We have two masses separated by a known distance. What's the gravitational force between them? Duh. So why not start simple, right? Fg is G m1 m2 over r squared. Let's see. So we have, well, gee, all we got to do is plug and chug, as they say. 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times 40 kilograms times 25 kilograms divided by 2.5 meters. Don't forget to square the separation. And yes, you do need to, put those units in. People, for whatever reason, just sometimes write newtons, right? G is not a force. You have to know those units. All right, so let's calculate, shall we? 6.67. Oh, you want to be sure you're doing this. Your calculator, when you type that in, ought to end up looking like this. All right, if you're typing 6.67 times 10 raised to the negative 11th, that's going to lead you to potentially some pretty big problems as we move forward. Make sure you're doing it this way. If you don't know how, you have to ask me tomorrow. Okay? Okay. E negative 11 times 40 times 25, times 25 equals, divided by parentheses 2.5 squared equals. So we get a paltry 1.07 times 10 to the negative 8th newtons. That's a small force, right? Oh gosh. So, right, a 1 kilogram mass weighs 10 newtons, or there's a force of 10 to the first newtons exerted on it. This is a billionth of that. Okay? So it's a little tiny force. Is it there? Sure, it's there. It's not zero, but it's small. Okay? And this really gets to the idea that most forces are pretty small, unless you're dealing with A, big masses, or B, masses that are really close together. All right, only way to get gravitational forces that aren't really, really small. Okay, and which object pulls with more force? The bigger one or the smaller one? We got to know this one. Same. Each exerts the same. This is the force that the 25 exerts on the 40. This is the force that the 40 exerts on the 25. They are the same exact force. Okay? Okay. Here. Oh, yeah, we might as well do this. Good one here. All right? Part 1. What do you call it? Multiple choice, right? These are hugely popular questions, right? Assuming you know this equation, which you will, which you now do, right? What they will ask is, we'll say something like a force F attracts masses 1 and 2 when they're separated by a distance r. That's sort of your given. What would happen to what force would attract the masses if m1 was tripled? Well, a lot of you will see that, well, if you triple one of the masses, obviously that's going to triple the force. Now, some of you won't see that, but here's a way you can Here's a way you can get, sort of maybe get around that if it doesn't just come to you. All right. One, here's what I would do. Let's say that make everything 1, right? If in the first case, f is g times 1 times 1 over 1 squared, well, that's just g. Okay. Well, what if I triple one of the masses? Well, now it's f is g times 3 times 1 over 1 squared. Well, that's 3g. What did I do to the force F? Oh, I multiplied it by 3. So the result is 3F. Now, I hear you. You said, I thought it was 3g, but I'm saying it was a force F. What happened to the force? It went from g to 3g. It's multiplied by 3. So what did we do to force F? We turn it into force 3F. Okay? Okay. What if we were to cut m1 in half, or halve it, and quadruple the other one? Well, cutting one in half would make the force half as big. Multiplying the other by 4 would make it 4 times as big. Combining those, you get that we would multiply the whole force by 2. If you want to plug those numbers in to prove it to yourself, be my guest. What would happen if we doubled one mass but halved the other? Well, those would sort of counteract each other. We end up with the same old force, F. Fair enough. Ooh, what happens if we change R? Here's where we're going to get you. We're going to get you. All right, now, first of all, if R... Sorry, I just made myself laugh. If R gets smaller, right? R is cut in half. If R gets smaller and R is in the bottom of the fraction, F has to get bigger. So we cut R in half, we double the gravitational force, right? No, we don't double it. And why not? Because of this. So whatever we do, so the inverse part, the fact that R is in the bottom, means whatever we do to whatever we do to R, we do the opposite to F. If we divide R by 2, that means we multiply F by 2, except by 2 squared. All right, so our result here, is 4F. I'll do that again. Whatever we do to R, we do the opposite to G. Sorry, to F. Whatever we do to R, we do the opposite to F, except we do the opposite squared. Right? Let's look at this one. Oh gosh, let's look at all these. You look at all of them. Why don't you? You ought to pause. You ought to fill all these out, and we'll get back together. All right, ready? Pause. Welcome back. You didn't pause, did you, you cheater? Pause. I'm kidding. You must have. I know you did. So, all right, let's do this. Let's look at these. Yeah, okay. So we double M1. What would that do to the force? Well, if we double M1, that would multiply the force by 2. If we cut R in half, that would, as we said, multiply the force by 4. Well, what's the total result? The total result is we get 8 times as much, right? You double it, then you quadruple it. That gives us 8 times as much. Not 6 times, right? 8 times. Times 2 times 4 is times 8. 8F. All right, let's triple M1. Well, that would give us 3 times the force. Let's triple R. Let's see how well we figured this out from our first discussion of what happens when you change R. If we triple R, R gets 3 times bigger. F gets 3 squared times smaller, or times 1 over 9. Catch that? R gets 3 times bigger. F gets 3 squared times smaller, or 1/9 as big. So we multiply by 3, we divide by 9, that gives us a force of F over 3. If you got that, you rock. Oh, baby, what happens if we change all 3 things? All right, you quadruple one mass. That's going to give us, well, 4 times the force. You double another mass. That's going to give us, oh gosh, twice the force. You cut r in half. Boy, we keep doing this with r and halving. Well, that's going to give us 4 times the force. So that's a hefty 32F. And the last one. Well, half one of the masses. Well, I'll do this a few times. You half one of the masses, that's half the force. You double the mass, you double the force. You double R, R gets 2 times bigger, F gets 2 squared times smaller, or 1/4 as big. Total answer, F over 4. Again, folks, if these are tricky for you, just go up to here and do them with numbers. Start with simple numbers, with ones, make simple adjustments, see what happens. Okay? Huh? Huh? Not bad, right? Gravitation? We'll get to this stuff tomorrow, probably. What's after that? I don't know. Yeah. Yeah, good place to start. We'll have some problems, some gravitational problems to solve tomorrow. And hopefully we'll see if we have your test done. No promises, but I hope so. Okay, peace out.